That if, like me, you spend a lot of time teaching calculus, which is you spend an awful lot of time doing these particular, very specific methods to calculate various kinds of integrals, and it might seem like you've got quite a good thing going on, but what you notice somewhat easily is that if you change the situation even slightly, then you can't calculate the integral. You can't explicitly get the integral. So this hodgepodge of different techniques: integration by parts, use substitution, trigonomic substitution, rational functions. All this different techniques you learn in calculus only work when you're in the very narrow circumstances where you can apply them. And if you have rather natural-looking integrals, then suddenly nothing that you know, nothing that you teach, that you spend weeks teaching calculus students how to do, is of any use. And with this bunch of techniques, suddenly you're wildly expanded in what you can actually calculate. So this is thinking from the perspective of as I said before, of 18th century mathematicians. This was really, really striking and impressive for them. And now, as I teach it now, after many years of teaching calculus, I see that more precisely. I see that more clearly, because we want to integrate something like this: 0 to 2 pi f of cosine of theta, sine of theta, the theta, where f is, I'm not going to be too specific, f is a nice function, f is analytic in both of its variables here, okay? And we're going to find out it's possible to turn this thing into a holomorphic function in the following way. So let me just say f is very nice. And what we're going to recall is how we formulated the trigonomic sine and cosine. So recall the following. If we do this, do e to the ix, recall it is cosine of x plus I sine of x. So therefore, e to the ix, that's plus e to the minus ix over 2. Since sine is odd, this thing will just become cosine of x. And similarly, e to the ix minus e to the minus ix over 2i. This becomes sine of x. And that's how we created the trigonomic sine and cosine. So the complex sine and cosine. Defined like this. So cosine of z is e to the iz plus e to the minus iz over 2, and sine of z equals e to the iz minus e to the minus iz over 2. The stuff we saw already. All right, so we'd like to replace this stuff by something which is going to turn out to be a function which is holomorphic except for some singularities that turn out to be poles. That's going to be our mission. Yeah? So that means somehow rewriting the cosine and the sine using this stuff here. And there's a trick here. There's a trick. So what we're going to do is we're going to say, okay, let's consider the integral around the circle of f of z plus z to the minus 1 over 2 and z minus z to the minus 1 over 2 like this. So I'm going to add some things to this later, but let's just, I want to give you a way to recapture how we do this, how we get it into the right form. And the trick to consider is we're gonna try and replace this thing by the integration around the unit circle of something like this. Okay, something like this. But so let's see what happens if we do that. See how close we get to recovering this expression from this expression. Let's see what happens. So take parameterization. So this thing we're about to work out. So take z of t. Of course, it's going to be equal to e to the it. So z prime of t is equal to I e to the it, like this. Yeah. So you're going to think about this in the following way. So if we now turn this thing into the parameterization, so at the moment it's just dz, and I'm going to put some stuff in later. So then we go 0 to 2 pi. Then we're going to have f of, now z becomes e to the it plus e to the minus it over 2. And then we're going to have e to the it minus e to the minus it over 2i, like this. And then we're going to have whatever we put here, and then z prime of t, which is just I e to the it, like, oops, it like this, and dt. And because this thing just becomes cosine of t, and this thing becomes sine of t, we get close to what we want. We get close to what we want. So we get this thing, oops. We get this thing out of this thing like this. Except that we have this term right here that we do not want. We have this term right here that we do not want. Yeah? So if instead of considering this guy right here, what if we considered this function, 1 over iz, like this? Yeah? And if we did that, then what would happen? Then we'd have 1 over I, and z is e to the it. And then these e to the its would cancel, and then we really would get exactly what we want. Do you see what I mean? Yeah? So you can get the right form from just saying, okay, let me look at this part, and with the memory that I'm going to integrate around the unit circle, and then get the sine and cosine from this stuff here, which is the standard way we define this trigonomic sine and cosine. Then you almost get what you want, except that you have this extra term. So then you go, okay, well, then instead of integrating that guy, I'm going to make a modification so that when I put in the parameterization, then the stuff I don't want actually cancels. Yeah? The stuff I don't want actually cancels. Yeah? All right, so with this trick, what have we learned? We've learned that this guy that we're interested to calculate now becomes this guy here. And if f is nice in the sense that this expression over here turns into something which is holomorphic except for some singularities inside the unit ball, where the singularities are just poles, then this is going to be a nice thing that we can apply the residue theorem to. This thing here is now accessible to us via the residue theorem. Yeah? And it turns out that there's a rather wide class of f, such that when you create an expression like this, it is indeed going to be something which is going to be a nice holomorphic function, except for finitely many singularities inside the ball. Yeah? So it's the class of f for which this will work. I mean, you can sort of see just algebraically that if you take any kind of polynomial function of both variables, then for sure that's going to be fine, right? Thinking a bit more generally, if you take any kind of rational function of both variables, that's going to be fine. So that we have really a huge class of f for which we can actually do this method. So whenever you see this question and you're asked to integrate around 0 to 2 pi some expression of sines and cosines, it's got to be this. It's got to be turning into this. Okay? Cool. All right. So let's do an example. This example. Example 1. Let's integrate from 0 to 2 pi 1 over 2 plus cosine of theta squared d theta. And notice that we are indeed out of the realm of stuff that we can apply. This is a nice looking integral, not very complicated, but there's none of our many calculus 2 methods are actually going to help us here. There's no u sub, there's no integration by parts, there's no trigonomic substitution. This is already just completely out of the realm of the toolbox of calculus. Huh? But this is obviously a fairly nice function in terms of f. Yeah? In terms of f. This will indeed be good enough for us. So we are going to do this stuff. So this guy, let's put it over here. We're going to turn it into an integral around the complex numbers, around the unit circle. Okay, so what is our f? Our f is just this guy. So this cosine of theta, we're going to replace by 2 of z plus z to the minus 1 over 2, like this. Yeah? And then we have to add this term over here, 1 over iz, and then now we get this. So this is just the application of this stuff I've done here, that this integral turns into exactly the integral that we want. Are you happy with this? Give me a thumbs up if you see why this turns into this via this. So, let me clean the board and then we'll do it. We were doing this, right? We had 1 over 2 plus z to the minus 1 over 2, like this, squared, and then 1 over iz dc. That's where we were. Yeah? Cool. So we want to try and make this dz into as nice a form as possible so that we can see what the singularities are inside this thing and then apply the residue theorem. Yeah. So what do I want to do? Let me first of all take out the 1 over I, which is the same as minus I. Is 1. I want to multiply top and bottom by z so that I can get rid of the z minus 1. And actually I want to multiply top and bottom by 2z so I can get rid of the 2 here. So then I'm going to have 2z on the top. And because I have a z here, I'm going to have 2z squared. Actually, I want 4 because I want to take it inside the square root. So let's put a 4 here. And then I'm going to have a 4z squared outside of this, which I'm going to part. Well, let me do it in stages. So I'm going to have 4z squared outside like this. And then I'm going to have 2 plus z to the minus 1 over 2 dz, like this. Yeah? Everybody happy? Okay, Laura? Yeah? Okay. So, then what? So I'm going to take out the 4. So let's write this out as minus I over 4. 1 over I is minus I. We're integrating around the unit circle. S1. And let's take this, oops, I've missed out the squared sign. Let's take this through the square. So we're going to have 4 outside here, which actually, I mean, it's going to cancel, so why do I need it? Let's just get rid of it. Set like this, and, oh, sorry, stupid. We do indeed have the 4, because I'm taking the 4 through this. So then when I write this thing as 2z squared, then I take it through. So then I'm going to have 4z, and then I'm going to have z squared plus 1, like this, dz. And let's put the stuff correctly back. So that's minus I. Yeah, that's correct. So what have I done? I've just written the I as minus I, and I've multiplied the 4 through this thing right here. Yeah, and that's all I've done at this point. And that looks good because now I have a quadratic on the bottom here. Oh, everything should be squared. I keep forgetting this. Now I have a quadratic on the bottom here, so I can actually factor it. Yeah, so z squared plus 4z plus 1 factors, and the factors turn out to be like this. Z minus 2 minus root 3, Z minus 2 plus root 3, like this. These are the factors. And these are annoying to write out because they're long, so let Z0 be minus 2 minus root 3, and let Z1 be minus 2 plus root 3, like this. And then we can rewrite this guy as minus I, the integral around the circle. Actually, now I want to take out the 4. Why not? So minus 4I z over z minus z0 squared z minus z1 squared dz. Yeah? And this is going around the circle, so let's draw a picture. This z0 is minus 2 minus root 3, so it's way out here. It's not inside the circle. Yeah? But this guy, minus 2 plus root 3, actually will be inside the circle. Yeah? So we have z1, it will still be negative. z1 is here, and z2 somewhere over here. We don't care about it. It's outside. Yeah? Cool. So the only singularities of this nice function, which is holomorphic except for some singularities, and the singularities are poles. The only pole we have to care about is at z1. Yeah? The only pole we have to care about is at z1. Cool. All right. To simplify notation as well, let's just write f of z is this function. Okay, this is our nice function. And then by the residue theorem, this thing is minus 4i. And then the residue, or 2 pi I, times 2 pi I, the residue at the point z1 of our function f of z. Yeah? So we need to calculate the residue. Yeah, I need to calculate the residue. So need okay, how are we going to do this? What kind of singularity do we have at z1? Yeah, it's an order 2, right? So we're going to have to use the formula to calculate the residues, right? So tell me about the formula. What did we have to do to actually calculate the residues when we have a pole of order n? In this case, n is 2. What did we have to do? In this case, just one derivative, but derivative of what? Good. So this thing, and there's some other part, there's one other thing you're missing. Factorial is going to be 1. What other thing? Good. Take the limit as z goes to z1, and then we're going to differentiate one time, and we're going to multiply, I have to rewrite this entire thing, our function by the pole to the power 2, times the function itself, like this. And we would be factorizing, we'd be dividing by n minus 1 factorial, but n is just equal to 2. So that is, n minus 1 is 1, 1 factorial is 1. So we don't have to care about this. So this is the thing we actually have to calculate. Yeah? Cool. All right, so let's take a look at this. So then we have d by dz. When we multiply z minus z1 through this thing, we're just going to have z over z minus z0. Yeah? So it's going to be this thing, z minus z0 squared. And then we just have the quotient rule. So this thing, put everything under the bottom squared. So now it's power 4. Differentiate the top guy, leave this bottom guy alone. Minus, leave the top guy alone. Differentiate the bottom guy. Let's clean that up a little bit. So we can factor out a z minus z0 from everything. So then we're going to have z minus z0. And then we're going to have minus 2z. And then on the bottom, we're going to have z minus z0 to the power 3. And then that has a nice form of minus z0 minus z over z minus z0 to the 3. Yeah? Cool. All right. And then we want the limit of this thing. So limit as z goes to z0 of this expression here in the red box. Oops. No, not Z0, Z1. Okay, so we are going to get minus Z0 minus Z1 here, and then we're going to have Z1 minus Z0 to the power 3. Okay, let's see what this is. So this is Z0 and this is Z1, so Z0 plus Z1 is equal to just minus 4, right? Because the roots will cancel. So minus this will just be 4. So we have 4 on the top right here. And Z1 minus Z0. So Z1 is this thing, and we subtract Z0. This is Z1, we subtract Z0. We are going to have just 2 root 3, like this. Yeah. So we're going to have on the bottom here 2 root 3 to the power 3. So what's that? That is 4. 2 to the 3 is 8. And then 3 to the power 3, so that's 3 squared times root 3, so that's 3 times root 3. And what is that? That is, that's just going to be 1 over 6 root 3, right? We are not done, because what have we done? We've just calculated what the residue is, right? This is just a calculation of the residue. So an easy mistake to make would be to think that this is the answer, but we're not there yet, right? So this is just the residue. Yeah, that's where we started, is equal to this thing. We took the derivative, we took the limit, so let's put in that this is the residue at z1 of our function f. But the actual answer we're looking for is, by the residue theorem, minus 4i times 2 pi times this thing. So the actual answer to our integral, which is no longer here, maybe I just put it back in, I remember it. So the actual answer to the integral, which is equal from 0 to 2 pi of 1 over 2 plus cosine of theta squared d theta, is equal to, so what's this going to be? So I squared is minus 1, so it's going to be 8 pi times this thing, right? So it's going to be 8 pi times 6 over root 3. So that's going to be 4 pi over 3 root 3. And that's the answer. So we can explicitly calculate this real value integral around the circle that is inaccessible by other methods through the complex world, through turning this into a holomorphic function. Okay? Cool. And we're later going to learn to integrate indefinite integrals involving a sine or a cosine in a completely different way. So, and the initial idea is completely different as well. So you're going to have to distinguish between this method and the next method rather carefully. So this method uses the fact that we can recover the expressions of sine and cosine from these guys. Again, we do this again. E to the ix plus e to the minus ix over 2. And the idea is that we parameterize around the unit circle, and then this thing becomes our parameterization, so then the cosine expression becomes things like this. Okay? That's the main idea. And once you have that idea, then you try it, and then you see that you get an extra term, and then you just correct out for the extra term by dividing by 1 over iz. Okay? So the two ideas, or maybe the one idea you need to do this kind of thing is we're going to turn it into an integral around the unit circle using this identity, using the fact that z of t equals e to the it is the parameterization we'll use, so that this cosine and sine, in this case cosine, can get turned into this expression. Then just try it and then find out that you need to correct it a little bit. Okay? Okay? So try and do it that way. Don't try and memorize the form. Try and memorize the strategy, and then you'll be more confident about it and more likely to get it right. Okay?